So we covered quite a bit of material. I really tried to emphasize the concepts and the approach behind the log mean temperature difference, overall heat transfer coefficient, and effectiveness NTU method. Today I'd like to spend some time solving at least one, hopefully two problems. So the effectiveness NTU method, it seems a little more disjointed, but once you solve a few problems with it, it seems to flow pretty well. So what do we have in it? We have the NTU. What is the NTU an abbreviation for? Number of transfer units. And the first time you think number of transfer units, it's really the thermal size. It's the thermal size. How big is it and how large is U? It's defined number of transfer units as UA over C min. So it's physical size, thermally, how well it transfers. So if I have a large U, it's pretty good at transferring heat for that size, or for any size. It's heat transfer per area. And then it's normalized by the minimum heat capacity rate. So this really is the thermal size. The effectiveness, what is that? Effectiveness is Q over the maximum possible if you let that same heat exchanger with the same inlet temperatures and flow rates go to infinite size, infinite area. And so this really is the rate. So the rate of heat transfer is embedded in the effectiveness, and the thermal size, or the area, is embedded in the number of transfer units. And you can look for an equation such that if given the size, you want to calculate the rate, you can find the effectiveness as a function of NTU for a whole host of heat exchanger types. Or if you give the rate, like I need this is the rate of heat transfer that I need to accomplish, how big of a heat exchanger do I need? Well, then you can look for a correlation where you get the number of transfer units as a function of the effectiveness. A little abstract maybe, but if you work a few problems, you see how it comes together. Again, here are the tables where effectiveness is a function of NTU. You see the pattern. Effectiveness, 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 function of NTUs. And likewise, another table for just the opposite. NTUs is a function of effectiveness for the same heat exchangers. We went through this derivation last time. It's a lot of algebra. It's tedious, but it's repackaging terms such that you get that nice relationship where you can get NTUs as a function of the effectiveness, likewise the opposite. This is the switch for the counterflow concentric tube heat exchanger. Let's solve this problem. A concentric tube heat exchanger with thin-walled inner tube operates in a counterflow mode. Help interpret what that term right there, thin-walled inner tube, mean. Thin-walled. It's going to be a negligible resistance to conduction through that wall. And there's really no difference between the fluid flowing on the inside of the tube and the fluid flowing in the annulus, which would be on the outside of that tube. So it has a 25 millimeter inner tube diameter and 45 millimeter outer tube diameter. Sometimes you sketch it like this and then like this, so the inner and outer diameter. So I have some fluid flowing in the tube, some fluid flowing counterflow in the annulus. Okay, where is the heat transfer occurring? Is the heat transfer occurring from here to there, and you have a convection to get it to the tube surface and a convection resistance to get it off of that tube surface to the fluid in the tube? Yeah. So you might want to think 1 over U is 1 over H on the inside plus 1 over H on the outside. That's a pretty simple equation for the overall convection heat transfer coefficient. What does it neglect again? Resistance in the wall. And what is the difference between the area on the outside and the area on the inside of that thin-walled tube? They're the same. And so I don't have to struggle with what area do I put here and here and here. Do I put area inside, area outside, and then area inside or outside there? They're all the same area if it's thin-walled. True? So a lot of times it's a little simpler like that. Is there a heat transfer across the larger, the 45 millimeter outer diameter tube? Is there a heat transfer across that tube surface? No. It's well insulated. It's what you might call an adiabatic heat exchanger. If you took me for thermodynamics, I said that can be a tricky term. Adiabatic heat exchanger. It's like, hold it. Well insulated heat exchanger? How does that make sense? Well, it's well insulated with respect to the surroundings, and inside of it there's a lot of heat transfer between a hot fluid and a cold fluid flowing inside of it. So I like to draw like this for the heat exchanger. Kind of put it like this. Maybe put the hot fluid flowing that way if you like. Put the cold fluid flowing that way if you like. And talk about the hot in and the cold in, etc. So we have water at 0.2 kilograms per second at 25 C enters the inner tube. So after I read the problem a little bit, the temperature of the cold coming in is 25 degrees C. And we have the mass flow rate of the cold is 0.2 kilograms per second. All right. Then we have oil. So this is water. And then we have oil for the hot fluid. And we have oil at a mass flow rate, m dot h is 0.1 kilogram per second. And it enters temperature hot in of 130 degrees C. And it's flowing through the annulus, but it really doesn't matter which one's flowing through the annulus, which one's flowing through the tube, unless they give us more information. But here it could be switched for this problem. And it exits, so we have the temperature hot out of 70 degrees C. The overall heat transfer coefficient, U, I'm not going to rewrite that, but is given in the last sentence. U is equal to 110 watts per meter squared degree C. They give us all the properties: mass density, specific heat, the kinematic viscosity, the thermal conductivity, and the Prandtl number. And for our water, as well as for our oil. And then they ask for part A, calculate the rate of heat transfer. What is the symbol for the answer for part A that we want to calculate? Q. And what would be the units for the answer for part A? Watts or kilowatts, something like that. How would you solve for it? I'm going to pause. I'm going to walk around and see how far you get on this one. All right, so a lot of us don't want to overlook the obvious. You can calculate Q one of three ways. From the perspective of what comes out of the hot, from the perspective of what goes into the cold, as well as a rate equation, which is limiting. That's the hard one. So the easy one here is, if I wanted to calculate Q, I know the mass flow rate of the hot fluid, the specific heat of the hot fluid, the temperature hot in minus the temperature hot out. True? Yes. And what did we calculate when we threw our numbers in? What did we get? 11,400 watts or 11.4 kilowatts. True? Is that what we calculated? Very good. Now on to part B. Outlet water temperature. How are we going to calculate the outlet water temperature? I'm going to pause, walk around, and see how you do. All right, for part B, so what we have is Q is equal to what goes into the cold. And what goes into the cold is mass flow rate of the cold, specific heat, constant pressure of the cold, temperature cold out minus temperature cold in. Hence, the temperature cold out will be the temperature cold in plus Q divided by, if you like shorthand, you put heat capacity rate of the cold fluid, cap C of the cold fluid. But that's just the product. And so when we run that number, the temperature of the cold out comes in at 38.6 degrees C. True? Very good. Thank you. Good. Very good. Okay. Now the last part is a little harder. We want the length of the heat exchanger. So if you could calculate the length of the heat exchanger, it'll take you a little bit longer, but please try that. So what we did was we calculated right here that the temperature of the cold out was 38.6 degrees C. So what I would do is I'd say delta T1 is the temperature difference between the hot and the cold on that end. And the delta T1 would be 130 minus 38.57 or 91.43 degrees C. You see how I get delta T1? And they come over here on this end, delta T2 on that end, temperature hot out minus temperature cold in, 45 degrees C. I would actually encourage you on exams and homework to do that, like those steps. Because sometimes people get all discombobulated and they say, oh, I just put the temperature hot where it needed to be the cold, and it keeps you from making a mistake. Once I have that, can you calculate the log mean, delta T log mean? That would be maybe delta T1 minus delta T2 divided by the natural log of delta T1 over delta T2. Make sure that the first time you try to calculate the log mean temperature difference isn't on the next test. Yeah, you want to have that down. How many people can calculate it? What do you get for this problem right now? 65.5. Professor, do I have to put all these in Kelvin? No, you don't. It's a temperature difference. Okay, it's a temperature difference. So now that I know what is the delta T log mean, I go back my rate equation. Q is equal to UA delta T log mean. I kind of put check marks. Do I know Q? Sure do. Do I know U? Hey, it's given to me in the problem statement. Did I just calculate the log mean temperature difference? I can now calculate the area from that equation. True. That equation is like the first two equations that we used for part A and part B, but it's the rate equation. The other were just conservation of energy statements. So this is really a rate equation. We calculate that the area comes in at 1.58 meters squared. That's how large I need to have it. And that area is made up of pi dl. Isn't that how we calculate it? Pi dl. So the length is the area divided by pi d. The length comes in at 20.2 meters. 20.2 meters. Look good? I wanted to also solve it using the Effectiveness Ntu method instead of the log mean temperature difference method. How would we solve it using the Effectiveness Ntu method? Well, you say the number of transfer units is UA over C min. So I'm going to be trying to get A. That means I need to get UA. That means I need to get NTUs. So it's kind of like I'm sizing it by finding out how big it is. Well, I look and I say for counterflow concentric tube, there's a relationship. The number of transfer units is equal to CR and effectiveness right there. So what is C sub R? C min over C max. And when I take a look at what was my minimum, the minimum comes from the hot fluid at 190 watts per Kelvin divided by the maximum, the cold fluid, 840 watts per Kelvin or watts per degree C, either one. It's a temperature difference. So the C sub R comes in at 0.2262. What about the effectiveness? I need the effectiveness. Well, it's the actual Q divided by Q max. Well, what was Q max? The minimum heat capacity rate times the temperature hot in minus temperature cold in. So the minimum heat capacity rate is 190 watts per degree C. And then the hot in was 130. The cold in was 25 degrees C. And so Q max comes in at 19,950 watts. So we had 11,400 watts, the actual, divided by 19,950 watts. Doesn't it seem like you're going a completely different route? We're going to get the same answer, but we're using the Effectiveness Ntu method. This comes in at 0.57143, so 57.143%. So put that in for the effectiveness there. put in for the C sub r there, and you calculate the number of transfer units. Comes in at 0.91611. Then I see that UA is equal to the number of transfer units times C min. And I calculate UA to be 174.06 watts per degree C. Then the area is UA divided by U. So we divide by the given U, which was, what was that, 110? And you come 1.5824 meters squared, same answer. You get length is area divided by pi d. And to complete it, it's the same. L is equal to 20.15 meters. So you can go either route. Once you get more familiar with effectiveness NTU, you typically prefer it. You typically prefer it. One of the advantages is they have these great tables where they have it, whether they want, NTU as a function of effectiveness, or the other tables where you have effectiveness a function of NTU. When is the real benefit? Is typically when you only know the inlet temperatures, not any of the outlet temperatures, so you have to calculate it. Then you get into the guessing and iterating game with the effectiveness, with the log mean temperature difference, but the effectiveness NTU is no iteration required. But you almost have to see that to understand that. We have a shell and tube heat exchanger that has 20 tubes, and each of the tubes undergo 2 passes through the shell. And there is 1 shell pass for the fluid on the shell side. So here's our typical shell, and we're going to have an end. Let me just put an end on it like this, and an inlet end, and this is divided, and we're going to bring some fluid in. All right. The hot water comes in, so I'll just color code it red. Then it goes into how many tubes? 20 tubes, and number of tubes is 20. Then it comes out and goes through 20 tubes out and collected and goes out. Okay. There's 2 passes through the shell. The first pass and then the second pass through the shell. It really doesn't specify if there's a U-turn here or if it just mixes as I've shown it. There's no distinction. All right. And the fluid on the shell comes in here and it's going to go out there. So it really only goes through 1 pass of the shell. Yes, there's some baffles to promote the flow going back and forth across the tubes. Like that. So the flow goes back and forth on the shell side across the tubes. The length of each pass is 4 meters. The tube has a 15 millimeter inner and an 18 millimeter outer diameter, and hot water at 0.4 kilograms per second. So the mass flow rate of the hot, which is water, is flowing at 0.40 kilograms per second in tube entering at 77. So it's flowing in the tubes, and it enters temperature hot in. Let me try and sketch this. Temperature hot in is 77 degrees C, and exits the temperature hot out is 37 degrees C. Oil is our cooler fluid. It flows in the shell side. The temperature cold in is 7 degrees C, and the temperature cold out is 37 degrees C. Calculate the convection coefficient for the tube outer surface. So first questions first, what symbol and what expected units for my answer? So we want to calculate an H, but it's on the tube outer surface. So any subscripts on that H? HO. And typical unit? True? Okay. Now, it's going to be a long route to get H naught, but it's embedded in the overall heat transfer coefficient U. And so we recall the equation 1 over the overall heat transfer coefficient is equal to 1 over the H on the inside, area inside, plus 1 over the H outside, area outside. And as long as that area matches U, a lot of times we don't put II on U and A or OO on U and A. We just match it as UA. That equation makes sense? So we can take into account the slightly larger outer diameter than the slightly smaller inner diameter of the tube. Okay. So if you want to calculate the convection coefficient on the outer surface, I would calculate UA and H in the inner surface. The areas on the inner surface, those are pretty straightforward, true? This would be the pi d on the inner, 2 L's because there's back and forth, and that's the area for one tube. And how many tubes do we have? 20. Would that give me the total area inner? And likewise, what about the total area outer? Pi d outer, 2L. Why 2L? Each tube has 2 passes. And then why n sub t? Why the number of tubes? Because there's 20 of them. Make sense? All right. Now, let's attack H inner first. How am I going to calculate the convection coefficient on the inside of the tube? It's forced convection, so we're probably going to check the Reynolds number, see if it's laminar or turbulent. If it's over 2300, turbulent. I'll look for a Nusselt correlation. The name of the most popular, easiest one, especially on exams in this semester, would be the Dietz-Bolter. That will give me the Nusselt number. Once I have the Nusselt number on the inside, I get the H on the inside. True? So, in order to get it, I need to get fluid properties. So what is the temperature average that I use to evaluate for the water? Because the water fluid properties are temperature dependent. It'll be the 77 in 37, add those two together, and divide by 2. That'll be 57 degrees C. And when I look in the table, they have it in Kelvin, so I add 273, it's 330 Kelvin, and it's a line in the table, and I'm so thankful. Because if it's a line in the table, do I need to interpolate? No. So I could just read off the properties. What properties are going to be needed to calculate that Reynolds number for flow inside of one tube? You can give me 2 favorite equations to calculate Reynolds number for flow inside a tube. Rho V d over mu, or true? Now, somebody says, I know the diameter inside, that's easy. That was 15 millimeters, 0.015 meter. I need to get the viscosity of the water at 330 Kelvin. 489 times 10 to the minus 6 units of Newton second per meter squared. And the mass flow rate, I have to think about this a little bit. Is it the mass flow rate of the water? They give it to me as 0.4 kilograms per second. But is that through each tube or just coming into the heat exchanger and then passing through, and separating and going into 20 different tubes? Each. It's a total mass flow rate. The water flow at 0.4 kilograms per second flows inside the tubes, but it enters at 77. But it's not, I know that it could be interpreted either way, but it's the total flow for all of them. So the m dot's going to be 0.40 kilograms per second divided by the number of tubes, and there's 20 tubes. So you divide by 20. 0.02 kilograms per second. And when you calculate the Reynolds number, we calculate a Reynolds number which is 3,472. How do I interpret that Reynolds number? Barely turbulent, but turbulent nonetheless. Okay. You could check the entrance region. How long will it have to go before it's fully developed inside each of those tubes? Rule of thumb. How long? It's turbulent flow. 10 Ds, 10 diameters. So the length for entrance is around 10 diameters. A diameter is 0.015, so it's a 0.15 meter length to be fully developed. It's 4 meters long. I'm going to neglect the entrance length. It's fully developed the whole length. True? So we calculate the Nusselt number, 0.023, Reynolds to the 0.8, Prandtl to either the 0.4 or 0.3. You look at the correlation, it's 0.3 when the fluid inside the tube is being cooled, not heated. The hot water is being cooled as it flows through the tubes. So we use the Didas-Boelter correlation. We calculate a Nusselt number, which is 22.1, the convection coefficient on the inside, Nusselt times K divided by D. You have to go back and get the thermal conductivity of water at 330 Kelvin, and you get the H is 956 watts per meter squared degree C. A lot of work to get H in her. So we finally got this term calculated. We're looking to calculate H naught. Everything in this equation I know except for UA. How am I going to calculate UA? Yeah, let's go ahead and use the Effectiveness Ntu method. So I'm going to have to make some more room here. I'm sorry. I'm just going to have to add another sheet, okay? So what I need to do is I need to find UA. To find UA, the pattern is the number of transfer units is UA over C min. Hence, if I could get the number of transfer units, then UA is equal to number of transfer units times C min, right? All right, how do I find the number of transfer units? Well, I'm going to look for a function of effectiveness and the ratio of heat capacity rates. Well, I'll have to calculate the heat capacity rate of the cold fluid. The heat capacity rate of the cold fluid is mass flow rate of the cold times specific heat of cold. And that comes in at 2231 watts per degree C. Heat capacity rate of the hot fluid is the mass flow rate of the hot fluid times specific heat of the hot fluid. Let me go back to my problem. The hot fluid was the water. I needed to get the specific heat at 330 Kelvin. What about the oil? I skipped that a little bit, didn't I? For the oil, you calculate the average temperature is the temperature coming in of 7 plus the 37 divided by 2. It comes in average of 22 degrees C, which is 295 Kelvin. And so we get the fluid properties for oil at that 295. So we can get for the oil the density, the specific heat, we can get viscosity, thermal conductivity, Prandtl number, whatever properties we want. All right. So that was for the cold fluid to give us the heat capacity rate of the oil is 2231. The heat capacity rate of the hot fluid 1674. So C sub R, the ratio is 0.75. All right, so we have this part. I need to get the effectiveness. The effectiveness is the actual Q divided by Q maximum. What is my actual Q? The actual Q is known from it's 66,944 watts. And the Q max is C min times temperature hot in minus temperature cold in. And that came in 117,152 watts. Hence the effectiveness we back calculate to be 57%. So we have now the effectiveness. Well, I have to go and I have to find the right correlation for a heat exchanger like this, where I have 2 tube passes, 1 shell pass. I can do it graphically. So what did we just get? We had about 57% for the effectiveness, so somewhere along this line. And what did we have for the ratio C sub R? 0.75. And so we can read off the number of transfer units, a little less than 1.5, 1.43. No, I didn't do that with 3 digits reading a chart, but you can read a chart and get close. Or you can go to an equation, shell and tube heat exchanger, 1 shell pass with 2, 4, or multiple tube passes. Well, we have 2 tube passes. It's a little step. You have to calculate this parameter E. If you calculate the parameter E, it comes into 1.4. When you calculate it, you put it up into this next equation for the number of transfer units. And there it's 1.4334. Too many digits, but there you go. So that's how you would calculate the number of transfer units. 1 shell pass, 2 tube passes. So we calculate this to be 1.4334. That goes into here with the C min. We calculate UA to be 2,399 watts per degree C, or Kelvin. So that's what I needed right here. So now I can go back to the previous slide. 2,400 watts per degree C. So we have 1 over 2,400 watts per Kelvin. You have 1 over H inner, 959. You had all that area inner. 1 over H outer, all that area outer. I'm going to skip over here. I hate to. Let me just give you the number. 7.5398 meters squared. Area on the outside. 9.0478 meters squared. Hence, you calculate from this equation right here, the H naught. H dot 397 watts per meter squared degree C. So I was able to do that today. Here, I didn't do it at 11 o'clock. Ran out of time. So sorry, I tried to speed up a little bit. Makes sense? Thank you very much. Enjoy.